Zaleski, who will give a very satisfying talk about satisfiability.
Okay, so like we said, it's about Boolean satisfiability. So first I'm just going to do some terminology. So suppose we have n Boolean variables. x1 through xn. And by Boolean variables, I mean each of these can be true or false. And I'm going to use 0, 1 to safe space. So we have n different variables, and they can each take on true or false values.
And true is 0.
Yeah, no, true will be 1 in my dimension. So true is 1 and 0 is false.
Just checking.
Yeah. And
Increment.
so a literal, so a literal is like basically a variable or its negation. So xi or not xi. So what I'm going to do is on the right hand side, I'm going to put examples of each of these things. So for example, a literal, you could do x1 or not x1. That would be an example of a literal. Okay. So we have 2 of those. And a conjunctive clause. Conjunctive clause, well, conjunction in logic means and. So it's going to be, you take an and of a bunch of literals. So for example, you can have x1 and not x2 and x3. So that's a conjunctive clause. And then you can do the same for or. So for or is like disjunction, so disjunctive clause. It is just going to be an or of a bunch of literals. So for example, not x1 or x4. Okay. And then you can have conjunctive normal form, or CNF. That is just, so now this is where it gets a little confusing. That's going to be an and of a bunch of or clauses. So it's going to be an and of a bunch of disjunctive clauses. So for example, you have x1 and not x1 or x2, and not x2 or not x3. So a conjunctive normal form is an and of a bunch of ors. And then, almost done with the stuff. So the last one, you can have a disjunctive normal form, or DNF. And so that's going to be an or of a bunch of conjunctive clauses. So for example, you could have not x1 or x1 and not x2 or x2 and x3. And for future reference, I'm going to be using these as examples. So let's call this example B, and then this one over here A. Okay, so that's all my terminology. Any questions about that? Okay, so now I can talk about the satisfiability problem. So usually I'll abbreviate that by SAT. And so the question here is given a conjunctive normal form in the variables x1 through xn. Is it satisfiable? So in other words, does there exist assignment to the variables, that makes it true. So is there a way to assign true false values to each of those n variables that evaluates to true? Any questions about that? So, for example, going back over here, so the example was CNF that I gave, A. So let's see if that's satisfiable. So you want to make this true, obviously you need to set x1 to be true. If x1 is true, then you go here, and x2 would need to be false. Because if x1 is true, then you can't satisfy that one. And then if x2 would need to be true, sorry. But then if x2 is true, then x3 would need to be false. Okay, so what I'm saying is example A is satisfiable. And you can see that just by letting the true false vectors be 1, 1, 0. So if I plug that in, I get a true statement. Okay. And let me give you an example that's not satisfiable. So another example, x1 or x2 and not x1 and not x2. This would not be satisfiable. Okay, because there's no way you can make all of these clauses true at once. Any questions about that? Very good. So, first of all, let's do this. It's called the Cook-Levin theorem. And this was around, I don't know when exactly it was published. It was published different from when they started working on it, but it was around 1970. They proved that this is an NP-complete problem. So they proved that satisfiability is NP-complete. So, and actually this was the first problem that was proved to be NP complete. So let's just real quick review what that means. So the NP part, right, NP stands for non-deterministic polynomial. So in other words, if you know the answer is true, right, like say I'm God and I know something is satisfiable, well then there exists a polynomial time way to show it's satisfiable, right, just by exhibiting the solution, right? So, like here, right, I exhibited an assignment to x that made it true. So, if you're God and you know it's satisfiable, you can give me a proof certificate that's polynomial time. So that is the NP part, and then the complete part says that basically this is like any other NP problem can be reduced to this in polynomial time. So this is like the hardest NP problem you can get. So in other words, that's saying that if there exists a polytime algorithm for SAT, then we know that P equals NP. So if you could come up with any polynomial time algorithm for this, then you prove P equals NP. And that's what we're going to do in this talk. Okay. So any questions about that?
Have you received the 1 million check?
No, not yet. We're waiting though. Okay. So actually, for the rest of this talk, we're going to be looking at the dual problem of this, which is tautologies. Hold on. Yeah. So this is equivalent to actually figuring out if something's a tautology. So let me show you what I mean. So note.
I have a question.
Yeah.
If I may ask. You've got 2 to the n. You've got n variables.
Okay.
So there are 2 to the n states.
Yeah.
So there are 2 to the 2 to the n possible terms.
Yeah.
Now that's
Like assignments to the
in your
variable.
CNF.
Oh wait.
It could be 2 to the
Oh, I see
could
what
be
you
some
mean.
of 2 to the
Yeah.
2 to the n
Right.
things.
Okay.
Okay. How are you going to check them in polynomial time?
What do you mean? So you're talking about this part?
God says this will work if we say
No,
x squared
polynomial is the length of the
of what?
f. It's also polynomial not in n, polynomial also in m, the number of literals.
It's not a polynomial in n.
No, a polynomial in m, the length of the formula. What you want is a polynomial time algorithm in m, the length of the formula, not in the number of variables.
Okay. So is that clear? I didn't get the question, but is it good now? Okay. So anyway, going back here, if we have a CNF, so notice that if we take its negation, it's going to be a DNF. That's just like De Morgan's law. So for example, if I take the negation of A, that turns out to be B. So if I negate this one, I get that one. And also so a CNF will be satisfiable if and only if the negation of that CNF is not a tautology. Okay. So there's going to exist a solution to this CNF if and only if the negation is not always true. Okay. So we can turn this into a problem where given a DNF, is it a tautology? Right. So tautology means that it's true for every assignment of truth vectors. Okay. And this is, like I said, this is just the exact same question, but for what we're doing, it helps to look at it that way. Any questions about that? Okay. So now let's look at one way to think of this. Suppose we take a random assignment of the variables, a uniform random one. So we pick, well, before I do that, let's suppose our DNF looks like this. So let's call it S, and let's say that equals C1 over all the way up to Cn. So in other words, let's suppose there are capital N clauses and C1 through Cn. Okay. And now let's pick an assignment to the variables uniformly at random. So we're going to pick vector x belonging to 0, 1 to the n uniformly randomly. And then the S is going to be a tautology if and only if the probability that S equals true is equal to 1. Okay. So we pick a uniformly random assignment. If the probability that it evaluates the true is 1, then it's a tautology, if and only if. Okay. And so now let's let AK be the event that a single one of those clauses is satisfied. So I'm going to let AK be the event that CK is evaluates the true. Okay. Then we can use, well, P of AK would be 2 to the minus size of CK. Right. So assuming that the variables in CK are all distinct, because you can easily reduce it to that case, right? The probability that you satisfy one of the clauses will be 2 to the minus the size of that clause. That's clear. Good. So then what we are looking for is the probability of the union of A, K. So we're looking for the probability that at least one of these clauses is satisfied. And then, so one easy thing you can do with this is let's just try the union bound. So this probability is less than or equal to the sum of the individual probabilities. So it's less than or equal to the sum over all the clauses of 2 to the minus the size of the clause. questions about that? Okay, so already this gives you one criterion to figure out when it is not a tautology. In other words, if this is less than 1, then there's no way this is going to be a tautology. So for example, if you have a 3 CNF, meaning that each clause is size 3, this would tell you, and suppose the number of clauses is less than 8, and this would tell you there's no way that cannot be a, there's no way that can be a tautology. I mean, okay, there's no way the DNF can be a tautology, so that would tell you this is satisfiable. Okay. So this tells you a criterion for when it's not a tautology. Any questions about that? Okay. So now what if we go further though? So this is just the union bound, which is, so this is basically, if you do inclusion, exclusion, and you only go one step, right? So now what we can do, the idea is to take this further, right? So in inclusion, exclusion, this is like the first term in the sum, but what you can do is start considering intersections of 2 sets, and then intersections of 3 sets, and so on. And each time you go up 1 step, the direction of the bound is going to switch. So what I'm talking about, this is the Growing Inequality. So the idea is we have that, so first of all, let me define A sub capital I to be the intersection J belongs to I of AJ. So this is just notation. Then we have that the probability of the union of AI is, I'm going to use this symbol because it could be less than equal or greater than equal depending on if it's odd or even. The sum I equals 1 to k, negative 1 to the I plus 1, sum capital I over subsets of capital N size I, probability of A sub capital I. Okay. And then this symbol, all I mean is this is going to be, let me think, less than or equal to k, less than or equal when k is odd, and the symbol is going to mean greater than or equal when k is even. So like up there, k was 1, and we got less than or equal. Okay. So again, that's just like inclusion, exclusion if you cut it off before you get to the whole sum. So any questions about that? So this is the idea of the algorithm that we tried on Maple. So the algorithm goes like this. You input your disjunctive normal form, and then, so we don't keep running and running, you also input a maximum k. So that's like how many steps you're going to go in inclusion exclusion before you just give up. So obviously this should be less than or equal to n, which is the number of clauses. And then the algorithm is just for k from 1 to the maximum. You compute a new term in that sum and add it on. And if at any step you figure out that your probability has to be strictly less than 1 or greater than or equal to 1, then you're going to just quit and return your decision and the k value for which we quit, just so we know how many steps it took. Okay, so this is the algorithm that we coded up with Maple. So any questions about that?
So you also return fail if you fail.
Right, so like, if you went all the way up to k max and you still didn't decide anything, then you would return fail. And then you could also, if you want, return the probability bound that you did get, even if it's not giving you a decision. So any questions about that?
Also get some bound.
Right, you get some bound that doesn't give you a decision, but maybe it helps you in some way. So, and then we tested this on a bunch of random input. So we tested this. The problem is, like, I was too lazy to find like an actual stat solver that works with Maple. So what we did is we tested it in, Maple has a built-in function to find whether a logical thing is like a tautology or not. So that's probably not optimal, but we tested it against that. And what we found is that it beats Maple when the number of variables is big compared to the number of clauses. Okay, which is like not surprising because if you look at this algorithm, it really doesn't depend on the number of variables, right? It's all about the number of clauses, okay? So what you can do, if you want to make a case where this does well compared to Maple, what you do is you take many, many variables, right? But you make the clauses not too big. Okay. But in general, we found that, like practically, I don't think this would be a great stat solver, but maybe in theory it's interesting. Any questions about that? Okay. And then one more thing about the solver, we also looked at, so given like the number of variables and the number of clauses, you can ask, what kind of cutoff do we need, right? So how big do we have to make that k max? So it's going to be upper bounded by n, because if you go all the way out to the maximum number, the number of clauses, then you just get the actual probability. But in lots of cases, you don't have to go through all the steps of inclusion and exclusion. So we did some statistics about how far you have to go before you get your answer. So we looked at the success probability. Given your cutoff value, k max. And we made some plots. So these are in my paper if you want to see better pictures, but basically we have this S-shaped curve. So what I'm going to do is plot the capital N, the number of clauses, on the horizontal axis, and then the y-axis is going to be the proportion. So we run it on lots of random input, and that's going to be the proportion where this worked. Okay. So I'll show you an example. Here's a curve. All right, we get like an S-shaped curve, and this curve represents when there is, say, n equals 20 variables, and our cutoff, k max, was equal to 4. And this inflection point turned out to be like n equals 15. So is everyone clear on what this represents? The y-axis is the proportion of the random input values that this algorithm gave us a conclusive decision, right? So one is like around there. Okay. So this is telling you that if you set your cutoff to 4, so you only do at most 4 steps of inclusion exclusion, then for the clauses up to around 15, this algorithm is pretty good. Okay. Any questions about that? And then we did this on different number of variables. So for example, if you do 100 variables and you set k max still equal to 4, you got something like this. So the inflection point didn't really seem to change if you make the variables bigger. Again, this is just like on a bunch of random inputs, so none of this is really rigorous. But empirically, this is what it looks like. Okay. But then if you So one more, if we make k max equal to 5 and say 20 variables, then you get this curve over here. So this is 20 variables, and you set your cutoff equals to 5, and then that pushes this inflection over to 20. And that makes sense, right? Because if you're making your cutoff higher, this is going to move to the right. But notice it moved to the right by more than 1, right? So that's our picture. Yeah.
So setting Kmax to an even number shouldn't make sense. It should really be the largest odd number, right? Because you're just looking for upper bounds.
Right, okay, so...
You're looking for most points.
Right, so this is just like the proportion of the ones that were a success, right? So you're right, if Kmax is even, then the ones that did succeed, the decision would have been true, right? Does that make sense?
Okay.
So we're counting if it gives you a conclusive yes or a conclusive no, we're counting that either of those is a success.
Oh, okay.
Right. Okay.
Yeah.
All right. So any more questions about this? Okay. So enough of that. And now we're going to look at a little generalization of this stuff. So I was going to continue this, but instead of using the Bonferroni inequalities, we can use the Laval-Volkel lemma, which was actually not that good in practice. But before I do that, I want to do something else that's like more interesting, and then I'll do that if we have time. So Dr. Z already talked about integer covering systems. Let me just remind you. So here are some examples of integer covering systems. So you could have 0 mod 3, 1 mod 3, 2 mod 3. You could have 1 mod 2, 2 mod 4, 4 mod 8, 0 mod 8, and one more. You could have 0 mod 2, 0 mod 3, 1 mod 4, 5 mod 6, and 7 mod 12. So these are just from Wikipedia. So each of these is an integer covering system because, for example, if you take the first one, any integer is going to be either 0, 1, or 2 mod 3. Any questions about that? Okay, and then here's some terminology. So a disjoint, or we're going to call it exact, it's the same thing. So an exact covering means that there is no overlap. So going back here, an exact covering means all of these arithmetic progressions are disjoint. Okay? So for example, the first two would be exact. Obviously this one's exact. It turns out the second one's also exact. And the last one turns out to not be exact because there's overlap. Any questions about that? And then distinct. Yeah, distinct. That just means all the moduli are distinct. So here you have 3, the modulus 3 gets repeated, so that's not distinct. 8 gets repeated, so only this one would be distinct. Okay, any questions about that? So then what we did is we took this and we generalized it to DNFs. So we're going to define what it means for a DNF to be exact and distinct. So let's start with distinct.
Analogized, not generalized.
Okay, right.